Okay, so what do we have here? We are going to talk about spanning tree protocol. So, so let me begin by just mentioning this is a adjusted topology from what we've been using before. I've actually simplified the topology. I removed the routed ports between distribution 1 and distribution 2. I've also reduced the number of VLANs. So really, we're only concerned about VLAN 10, VLAN 30. I put all these devices on VLAN 10, the 10.10.00/16 network, and all these devices on VLAN 30, the 10.30.00 network. What else? We are not running Ether channel here. I removed all that. I removed these as trunk links. So these are access links. We do have trunk links here. We are still running HSRP, hot standby routing protocol, as our FHRP, first hop redundancy protocol. So distribution 1 is the default gateway, acting as the active router for devices in VLAN 10. And distribution 2 is the active router for devices in VLAN 30, 10.30.00 network. And they are the standby routers for each other. Okay, so with that said, you'll need to notice some green link lights and amber link lights here. And that is spanning tree showing us the port states. I am going to keep this simple for both your enjoyment, and also Packet Tracer doesn't do everything perfect with spanning tree, so I'm not going to challenge Packet Tracer too much on our adjustments. But let's talk a little bit about what spanning tree is. Spanning tree is a network protocol designed to prevent loops in Ethernet networks to ensure what's known as a loop-free topology. The development of spanning tree was done by Radia Perlman, one of my heroes, and who took on the challenge of using a spanning tree algorithm to disable redundant paths. Basically, if you look at this, it's ensuring that between two switches, so these are all, think of these are all layer 2 switches, even these here, they're layer 3, but they're running layer 2 spanning tree. But between any of these switches, there is only one active path. So for right now, just realize that these amber lights mean that these ports are blocked. So we cannot afford frames to this port. We can, but it's not going to accept them. So think of this link as almost not being there. So that means, let's take a look from access 1-1, how does it get to access, let's make it this one here, access 1-3. Okay, it can't go here. This is a blocked port. So it's going up here to distribution 1, down here to access 1-2. Do I've got this right here? Oh, I'm sorry, up here to I'm sorry, let me do that again. Going up here to distribution 1, and then just straight across here to access 1-3. Let's take a look at access 1-2. How is it getting here? Okay, well, in that case, it can't go to distribution 2 because there's no way down to this path is blocked. So it's going to go up to distribution 1 and then over to access 1-3. So there's only one path between any two switches here. All right, a couple of notes here. Cisco runs what's known as Rapid Per-LAN VLAN Spanning Tree Plus, Rapid PVST Plus. This is a Cisco implementation of something known as Rapid Spanning Tree, which is an IEEE 802.1W standard. All right, what does all that mean? Rapid Spanning Tree added some enhancements for faster convergence over the original implementation of spanning tree. It also offers per VLAN spanning tree. What does per VLAN spanning tree mean? It's also an extension to the original spanning tree, which allows the running of separate instances of the spanning tree protocol for each VLAN in the network. What does that mean? That means we can actually have multiple root bridges, different root bridges for different VLANs. This will make more sense in a moment. Right now, we are running we're going to see we have a single root bridge for all VLANs, VLANs 10 and VLANs 30. There's also VLAN 1, which is a VLAN on our trunk links by default. But let's just focus on VLAN 10 and VLAN 30. And right now we have what's known as one root bridge. What does that mean? Okay, so over here on the left, okay, I have STP convergence. This is how spanning tree decides which links are forwarding and which ones are blocked, basically creating a loop-free topology. So if you see here, looking at where our green link lights are and our amber link lights are, we have no loops. Okay? There's no loop in our network. A loop would be something like going from let's go from access 1-2 to access distribution 1 to access 1-3 to distribution 2, back down to access 1-2. That would be a loop. Okay, but we do not have a loop here. Why? Can you see what's blocked? Oh, right here. That's blocking that loop. Okay, and that's true in any of these cases. Okay, so between any pair of switches, for example, between access 1-4 and distribution 2, notice it has to go via distribution 1, then down to access 1-2, and then up to distribution 2. Okay, this is blocked here because, again, we don't want to have any loops. All right, that said, how does the root bridge? So the root bridge is going to be the root, the center of our spanning tree topology. All other switches, also known as bridges, by the way. We'll go into that, but I'll have all this in my lab document. We used to call these things bridges or transparent bridges. Anyway, so you'll hear the term bridge used a lot with spanning tree. So one of these switches will be elected as the root bridge. All other switches will decide on one port that is their best path to that root bridge. So let's go through this. Elect one root bridge. So how is that done? Here's the 5-step decision sequence for these 3 steps for convergence. So the switch that's going to be the root bridge is going to be the one with the lowest root bridge ID. Now, what is the lowest root bridge ID? By default, we have something called a bridge priority, which by default is 32,768. So that's going to be the same on all of these. We can adjust that, and that's what we will do later when we want to select which switch is going to be our root bridge. But for now, they're all 32,768 plus the VLAN ID. So that'll make sense in a moment here. But for example, there are actually 2 separate fields, but Cisco, as we'll see in a moment, when it shows you the bridge priority, it'll show 32,768, and for VLAN 10, add a 10 to it. So it'll show it 32,778. And then the MAC address. So what if the bridge priority 32,768 is the same on all these switches? What's going to decide what is the lowest root? What is the root bridge? Which one of these will have the lowest bridge ID? Well, that's going to come down to the MAC address. Yes, switches have MAC addresses. One of the functions of a MAC address for that is specific for that switch is to give it a unique ID for spanning tree. Okay, so what I've shown you here is the MAC addresses for each of the switches. I'll show you how we can find that information. Well, I'll show it to you right now. We can find it very easily. All right, so I'm going to use another command here, show spanning tree, and I'm going to do VLAN 10. And what we can see here is it says bridge ID, okay? And right here, that's the address. That's the MAC address on distribution 1. Okay, so that's its MAC address. Each of these switches. So which one has the lowest? Can you see? Well, let's figure this out. Let's start here. 00600090. Well, this 60 is going to be lower than 90. I don't have to worry about the rest of these. 00, oh, wait a minute, 001, that's going to be lower than 60. It's going to be lower than 002. So far, this is the lowest that I can see. 001 is lower than 0010 or 000C. 1 comes before C. This is all hex. Okay, it's 0. This is still our winner. 001, lower than this, lower than this. So far, so good. Lower than this. Oh, we have another 001. Okay, let's see. Which one of these has a lower MAC address? 0014, 0016. Oh, looks like our root bridge is going to be this switch right here. It's going to win what we call the root bridge war. All right, and actually we'll see in a moment that we can see all of this happening. All right, we'll see that these switches recognize that distribution 1, this bridge ID. We'll talk more about that in a moment. All this information here, including the MAC address on distribution 1, that this is the root bridge. Whew. Okay, so next. Now we're going to look what's called root ports. Okay, so what is a root port? A root port is each switch's best path to the root bridge. Each switch will select one port as its root port. Now, these are gigabit links here. Okay, so path cost comes in effect here. And I won't go through this right now, but these are fast Ethernet. But right now, these are all gigabit links, so the cost is going to be the same. So looking at access 1, which one of its ports are going to be the root port? Well, let's go ahead and put them in there. So I'm going to make a little note here, put RP for root port. So this will be the root port. This is its best path to the root bridge. Oops, sorry about that, because this would be a longer path, of course. Okay, let's do another one. How about access 1, 2? Well, obviously, this is its best path to the root bridge. So let's make this the root port for that switch. I'll move it over on this side. Okay, let's do this here. How about this switch here? Well, obviously, this port is the best path to the root bridge. So this will be the root port. How about this switch here? Well, once again, we'll make this port here the root port. Now, how about these switches down? Well, yeah, let's go down here. How about these switches here? All right, well, both of these ports have equal cost to the root bridge. Sorry about that. So you can't use that. So then, well, how about sender bridge ID? This is the bridge ID of the adjacent switch or bridge. Well, that's going to be the same. Lowest port priority, we didn't adjust it over here. So it comes down to lowest sender port ID. So looking at that, we're looking right here. We're trying to decide which port is going to be the root port to get to this switch. The sender port ID here is port fast Ethernet 01. Here it's fast Ethernet 02. So 1 is lower than 2. So this will be the root port. And we'll do the same here. It's for all of these. They're all fast Ethernet 01 on the left, fast Ethernet 02 on the right. All right. We've got all of our root ports on all of our switches except this switch here. Okay, so let's take a look. Which of its ports has the lowest cost to the root bridge? And I'm showing you this, that they're all equal. All four of these are equal. Okay, so the lowest path cost to the root bridge is the same. So next step, well, what's the lowest sender bridge ID? Which of these four switches has the lowest bridge ID? Okay, again, we're 32,768 plus the VLAN, that's going to be the same on all of them. So again, comes down to the MAC address, 0060, 001, 0010, 00E0. This will be the lowest. Okay, so make a copy of that. This will be our root port. Okay, so this is the port it's going to choose to get to the root bridge. Okay. Now all of our root ports have now been selected. Okay, so what's next? Designated ports. So what is a designated port? A designated port is the best port on a specific segment to reach the root bridge. So let me start off with, and make it a little DP here for designated port. First of all, let's take a look at the root bridge. Which of its ports are, well, I'm sorry, let's look at it like this. On all four of these segments, which port, either this port or this port, for example, is the best port to reach the root bridge? Who's the closest? Well, nobody's closer than the root itself. On this segment here, who's the closest? Copy that. Again, whoops. I get that. Oh, let me move this here. Okay, there we go. Again, this port is the closest on this segment because it's on the root bridge. Oh, this is going to be a problem, Archie. It's going to be up. Let me move you out of the way for a moment. Okay, and I'll just put another DP here. There we go. Maybe I should just copy that one. There we go. All right. So all the ports on the root bridge will be designated ports. All right. So what else do we have here? Let's look at each one of these other segments. So each segment so far has these here have a root port, designated port, root port, designated port, root port, designated port, root port, designated port. Okay, we've got those links done. Let's take a look at down here. Okay, so on this switch here, it says, which of my ports will be the designated port for each segment? Okay, so on this segment, it says, so on this between FA01 and actually it's FA01 here, this will be actually the designated port. I'm closer than you are for this link. I'm also closer than you are on this link. So this port, this switch saying I'm closer than you are for this link and this link, both links. Okay. This is going to be true on all these links here. The level, what I call the level 1 access switch, of course, is going to be closer to the root bridge than the lower level 2 switch. Let's just do this one more. We're almost there. We're doing pretty good. Okay. We're doing pretty good. Let's take a look at how about these links here. Okay. So the links between distribution 2 and these switches here. Okay. Who's going to be the designated port? All right. So let's take a look at this link here. Is this switch closer to the root bridge or is this switch closer to the root bridge? Well, this switch says you're going through me to get there. So I'll be the designated port here. I'm closer to the root bridge than you are. Same thing here. This between this switch and this switch says I've got a root port directly to the root bridge. I'm close. You're getting there through me, so I'm the designated port. Okay, same thing here. I'm closer to it than you are. I'm right here. I direct connection to the root bridge. You got to come through me to get there. I'll be the designated port on this segment. This is per segment, per link. Let's do one more of these. Again here. So on this segment, I'm the designated port because I've got a lower cost to the root bridge than you do. So this is all based on lowest path cost to the root bridge. You or me, you or me, you or me, you or me. Now we're almost there, okay? Because we've elected our root bridge. We've elected our root ports. Each switch finds a port, best port to the root bridge, one port. And then each segment elects a designated port. The best port between those two switches, the lowest cost path to reach the root bridge. Now, what's left? Everything that's left is what we call a, well, in the old days would say non-designated port. Okay, but we also could call that an alternate port. Let me actually, where's my, here we go. So I'm going to just say non-designated port, or we could say alternate port. Okay, I'll say alternate. I'll go, there we go. Alternate port. Alternate ports are blocked ports. So everything else becomes an alternate port, which is actually blocked. We have some more down here. Let's not forget about these. So basically, if you're not a root port, you're not a designated port, you are a non-designated port or alternate port. There's how spanning tree determines its topology. Okay. All right. Okay, just pause to actually save this. All right, so, well, this is nice. You can figure this out if you have a topology, but how do you know all this stuff if you're not running around looking at link lights? Is there an easier way? Yes. So let's take a look at some spanning tree commands that give us this information. So let's just start here with distribution one. All right, so what I'm going to do first, let me get rid of that. I'm going to do show spanning tree summary. So this tells me a few things. It says switches in PVST mode. It's actually running rapid PVST plus. There's some things like port fast and BPDU guard we've talked about before, but it's running spanning tree for all the VLANs that it is configured for. So it has ports that are active, actually trunk links that are on VLAN 1, VLAN 10, VLAN 30, and VLAN 254, which is our native VLAN. All right, but what we really want to look at here is show spanning tree VLAN 10. Okay, so we can look at any of these, by the way. These will all give us the same information. But let's just use VLAN 10. So what is this telling me? First of all, that it is telling me, let's go down here. So the bridge prior, so here's its priority. It says 32,768, but it says 778. That's because we are looking at it for VLAN 10. So it adds 10 here. So that's how we get 32,778. Shows us right here. Priority 32,768 plus the VLAN ID of 10. Here's the MAC address. Okay. Now it also tells me who is the root bridge. Okay. Now, if we look at this, it says, oh, let's see, its priority is 3278. That's mine. Who's the MAC address of it? Hey, that's the same as my MAC address. Hey, this bridge is the root. I'm the root bridge. Okay. We can also take a look at these 4 ports here. Notice that they're all green, link lights are all forwarding, and they're all designated ports, just like what we saw. Pretty cool, huh? All right, let's go down here. Take a look at similar information for access 1. So access one says my bridge ID is 32,768 plus 10. So there's the 32,778. But here's my MAC address. The root bridge is 32,778. Again, 32,768 plus 10. And here's its MAC address. And we just saw that is the MAC address and priority and MAC address of distribution one. Now, if we look at these ports, okay, we can see which ones are root ports, which ones are designated ports. Notice that this port here, gig 01, that's our root port. Gig 02, that's our designated port. We can see that here. Gig 01, root port, gig 02, designated port. You'll also notice that all of these ports here are also designated ports. Okay. Even the ones that are connected to our end devices. Okay, these are all designated ports for that segment. Let's go down here. This is kind of cool too. Show spanning tree VLAN 10. Fast Ethernet 01. This was our root port here. Okay, the green link light. Here's our alternate port, which is in blocking state. That's the amber. That's our alternate port. Okay. So if this link goes down, by the way, if FA01 goes down, that link, then this port here, FA02, will become the new root port. Matter of fact, hey, we could probably do that, right? Why not? Let's do it. Make sure I don't delete the wrong one here. Let's just get rid of that. Okay. Spanning tree is converging now. It's going to take a few seconds. Okay. It's in the listening state. So it goes through these several states of listening, learning state. I'm going to go through all these, but right now it's not forwarding yet. Almost. Look at this. It's the root port. It's green. Isn't that cool? What if I put that link back? All right. I can hear you asking that question. Let's put it back. Fast Ethernet 1. Fast Ethernet 1. Okay. Spanning tree is reconverging here. Okay. So it's listening. It's alternate. So I said, oh, I got to block this for right now because I've got another port. I got to run spanning. Got to let spanning tree reconverge here. Learning on FA01, blocking here till I find out what's going on over here. Okay. Similar is happening over here, by the way. We're almost there. Let's take a look here. Okay, so you may be wondering, wait a minute, Rick, this swapped. No, this is what swapped. Packet tracer. Oh, I'm messing this up, aren't I? That's what it swapped. Okay, this port on the left is FA02. This on the right is FA01. Okay, so packet tracer swapped them there. All right. So not to confuse you. Okay, let's take a look. Let's go up way up here. Okay, let's look at distribution 2. Okay. So here, we've done show spanning tree for VLAN 30, or actually we can do it for, let's keep it for VLAN 10 here. Okay, it's the same. It's the same. Okay, again, this is my bridge ID. So 32,768 plus 10, 32,778. Here's my MAC address, but I know the root is distribution 1. I don't know that's the name of the switch, but we know it is it's MAC address. Okay, and we can actually see which ports at all these ports were alternate ports, right? Except for this one here. What port was that? Gig 104 connected to this switch, connected to this switch here. Again, this is the root port because it's best port to reach the root bridge because this switch had the lower bridge ID. Okay. Okay, the cost was equal to all four of these. Once again, this was the lower bridge ID, lower sender bridge ID. All right, let's go back to here. We can actually see this. Gig 104 is forwarding. The other ones are all alternate in blocking state. Okay. Now, I'm going to pause here just for a second. Okay, I wanted to bring up my little drawing tool here because I want to talk about what happens. Let's say this device here wants to send a packet to its default gateway, Ethernet frame, packet inside the Ethernet frame. It's a packet for a destination IP address on another network. Well, here's the default gateway. Okay, this is the active router for VLAN 10. Okay, so it's going to be able to send it here and then right here. Okay, and out it goes. Okay, that seems like the best path. Okay, but how about these devices over here? Let me use a different color here. For example, what about, let's pick on this device right here. Here's its default gateway. Okay, so what about sending a packet from here to a device on another network? Okay, encapsulated in the Ethernet frame of the default gateway. MAC address to the default gateway, this device right here, this layer 3 switch. It can't get there directly. That doesn't, here's its best path. Look at this. Here's the root port. So what it's going to do is send it here. Then it's going to come down here. Only one path between any pair of switches. And then here. Well, that's the long way around, isn't it? Same thing. So any of these devices here, by the way, same thing over here. It's going to go, try and make this not too messy. Also to this same layer 3 switch, no, same switch. Okay, just think of layer 2 here. It's just trunk links, then down here and up here, then to this layer 3 switch, the active router, the default gateway for devices in this VLAN or IP network. Not the best path, is it? All right, can we make this better? Yes, let's take a look. Okay, so I had mentioned earlier that Cisco switches run Per-VLAN spanning tree plus, actually rapid Per-VLAN spanning tree plus. Again, what that means is we can actually have different root bridges for different VLANs. This allows us to take advantage of some of those links that are blocked and make them active for some VLANs. And they'll be blocking for others, but and vice versa. So, vice versa. So when we create this, we're gonna have two different root bridges. Some links will be the forwarding links, let's just call it, to reach this as their way out for the devices on VLAN 10. For devices on VLAN 30, we're going to make this the root bridge for devices on VLAN 30. So those devices will be able to reach their default gateway directly. Let's see how to do this. So what I'm going to do here is I'm going to go to distribution 1, and I'm going to give the following commands. Oops, not that command. There we go. I'm going to make it the and make sure I've got these right here. Yes. Okay. Whoops, I spelled secondary wrong. There we go. So I've made it the primary root bridge for VLAN 1 and VLAN 10, and the secondary root bridge for VLAN 30. Okay. Over here, what I'm going to do, and I better make sure I spelled secondary right. Yes. Let's go here, config P, paste. I've made this switch the primary root bridge for VLAN 30 and the secondary root bridge for VLANs 1 and 10. So if there is a link failure, if this bridge, this switch can no longer be the root bridge, this one can take over and vice versa. All right, so let's just give it a moment here and let spanning tree reconverge. Okay, so we're seeing all green link lights. Well, it's kind of showing us all green link lights, just saying, yes, I am forwarding for some, but I may be blocking for others. So let's take a look here. So let's go here to this switch here. And if I do show VLAN, show spanning tree VLAN 10, okay? So it is the root bridge for that VLAN. Okay, so it's forwarding designated ports. So they're all designated ports for VLAN 10. But if I do the same thing on that same switch for VLAN 30, it tells me, hey, you know what? I am not the root bridge for that, for VLAN 30. Matter of fact, the root bridge, wow, look at that. Look at that bridge priority. Look how low that is. So the commands that we gave it, and I'll explain this, let me show you once again here. When we give these commands here, root primary and root secondary, it actually changes the bridge priority. Let's go back up here. You notice that when I did show spanning tree VLAN 10, the priority, no longer 32.768, is it? It actually lowered the priority to make sure, hey, I am the root bridge. Okay. For VLAN 30, I'm changing my priority, but it will be slightly different. Okay. Show you that. I'll mention more of that in a moment. Let's go over here to this switch here. Okay. So if I do N, show spanning tree VLAN 10, okay, nothing really changed for VLAN 10. Okay, it says I never was the root bridge. Here's the MAC address of distribution 1. Same ports are blocking and forwarding. Nothing really changed. Because I've got some green link lights. Why do I have green link lights? Because if I do show VLAN, show spanning tree VLAN 30, what it shows me here is, oh, look at these. These are all designated ports. That's why they're green, but they're designated ports for VLAN 30. So what does that mean? What that means is this. So these devices here are still getting to their default gateway directly, okay? But what has changed now is these devices here, to get to their default gateway, they are going this way. Per VLAN spanning tree, we have two different spanning tree instances, two different spanning tree topologies, two different spanning tree root bridges, one for each VLAN. Okay, now I want to mention that, let's take a look at distribution 1 and distribution 2 for VLAN 30. I'm going to move that right there and this right here. And I think we can see them both. Yes. Okay. So distribution 1 says for VLAN 30, okay, when we gave it the command to spanning tree VLAN 30 root secondary, okay, it changed its bridge priority to 28.702, 28.672 actually, plus then the VLAN ID. So I've lowered my bridge priority. That's going to make me the number 2 in the list. Why not number 1? Because we made this switch here, distribution 2, when we said spanning tree VLAN 30 root primary. Look what we gave it its bridge ID. We made it 24.576 plus 30. So it says my priority is going to be lower than yours. So that is why I am going to be the root bridge. Okay. So we've both been lowered. Me because I'm primary. So in primary, I'm going to be even lower than you who are secondary. We both got lower than the 32.768 by default, but I'm even lower because I want to make sure I'm primary. You're lower, but you're not quite as low as me. You're secondary. If I can no longer be the root bridge, you will take over. Okay. All right. Pause once more. Okay, so a couple last notes here. 1, it is important that you select your root bridge. Root bridge matters, the location of the root bridge. Typically, we want it near the top of our layers, or usually it's going to be our distribution layer switches. This is very important, as we saw, to make sure that these switches down here take the best path to their default gateway. Okay, so we want to make the distribution switches, the ones that are the active router for that VLAN, we want to make sure that it is also the root bridge for that VLAN. Once again, the router, the layer 3 switch, was the active router for that VLAN. We want to make sure that it's the root bridge for that VLAN as well. Now, the other note I want to just mention here is you can see this can get complicated. You can see, wow, think of even have more links, more connections. Spanning tree, great protocol for loop prevention, but predictability is not easy to figure out which ports are locking and forwarding just by looking at this without all these link lights can be very challenging, especially even more complex networks, especially in data centers. So what's the solution to that? The solution is start moving to layer 3. What if all these were layer 3 links? Then it just becomes basically basic routing. Okay, we don't worry about spanning tree convergence. The routing protocol will select the best path. We can have multiple active, we can have equal cost paths. We can have redundancy. We don't have to worry about, some ports being blocked. Everything is forwarding. Anyway, that's for another discussion. Okay, but this is part of that evolutionary process. Okay, that going from the days of just adding a switch because routing was hard. Now we're kind of going back to now we're going to routing because our switching topologies can become so complex, so unmanageable, so unpredictable. And things have also changed as far as the hardware. Used to be layer 2 switching was much faster than layer 3 routing. Now, because so much of the routing has been pushed down into the hardware, into the ASICs, application-specific integrated circuits, that using things like Cisco Express Forwarding and things like that I talk about in other classes or other labs, other videos, that basically routing is as fast as switching. Layer 3 routing as fast as layer 2 switching. All right, I hope this helped. Hope it helped a little to demystify spanning tree protocol for you. If you find this a little hard to figure out which does what, you're not alone. My lab document will talk about a lot of this in a little bit more detail, but this is remember your STP convergence, 3 steps, and how it decides which ports is which in each step is here's the 5-step decision sequence. All right, have a great day. Thank you.